Okay, here we have an introduction to nuclear chemistry, and I'd like to spend most of the time going over some examples. You can read through this, but knowing that Becquerel discovered radioactivity, he was aided with the help of Marie and Pierre Curie, and you should know the definition of radiation here, which is particles and energy produced when nucleus undergoes radioactive decay, as well as radioactivity. It's the spontaneous disintegration in which small particles of matter or electromagnetic radiation are emitted by unstable nuclei. And we should have a good understanding of the differences between chemical and nuclear reactions. Notice that in chemical reactions, you're only talking about rearranging of atoms and you form new substances. That's what we've worked with up until this point. And in the process, you get small amounts of energy that are either released or absorbed, and that's because we're only dealing with those valence electrons, the outer energy level electrons. In nuclear reactions, we're talking about going from isotopes of one element to isotopes of another element, and that's known as transmutation. And this can occur naturally or artificially. Naturally is just usually when you have these big, heavy, unstable elements that just break down or decay to form more stable nuclei. And then artificially it can be done either in a linear accelerator or in a nuclear reactor. And the big thing to note here is that we're talking about really huge amounts of energy that are involved in nuclear reactions. It's the nucleus of the atom that's breaking apart. It's not just those outer energy electrons. And you do not have this on your notes, but this is just a little reminder for you about nuclide symbols, and you've seen this. This was back in Unit 3 for us. We know that this is where we would write the symbol, and that symbol has been for an element up until this point. But we could really say it's for an element or a particle, because we're going to be looking at some subatomic particles as well. And we remember that it's the mass that is put up into the upper left-hand corner. And up until this point, we've really said it was the atomic number that you would put in the lower left-hand corner. But instead of calling it atomic number, I'm going to call it the charge, because it's really, we're just talking about the nucleus. So if you have protons and neutrons in the nucleus, the protons would have a positive charge to them. So that's what you would expect to have shown in right there. Before we talk about the different types of particles, I want us to make sure that we know whether or not these particles will behave as reactants or products. So if it says something about absorption of neutrons, for example, then that means that that would be a reactant. If it's neutron bombardment, well, neutrons are bombarding a certain substance, so that's, again, going to be a reactant. If you're capturing something, electron capture, that's going to be a reactant as well. If a particle decays, if it decays, it's given off or emitted, both of those are going to be products. So that's really important that you understand those differences to be able to work through some of these problems. And the different types of problems that we have are going to involve, here's the different types of particles that we have. And the first thing I want to make note of is beta particles, and they can be written. It would really be more correct if you're going to use the beta symbol. It would be more correct to put a negative in the upper right, like a superscript up there. So that's a beta particle, exactly the same thing as an electron, so you can write those symbols the same. And what we see is that they don't have great penetrating power. They can be stopped by aluminum or wood, so not great penetrating power. This type of information, I'm not going to go through that with each one of these, but what I want to show you is that if you understand, if I told you that carbon-14 undergoes beta decay, well, that means we start with carbon-14. It's got to have 6 as the number of protons, so it's charged down there. And if it undergoes beta decay, well, then it's going to spit out an electron, so we know that's over there. What we need to do is we need to figure out how that carbon-14 transmutates. And in order to figure this out, this number right here, the way we do that is we have to separate it by that arrow, and eventually I'm going to get to this in the next couple pages. We see that if the mass is 14 on the left-hand side as a reactant, it's got to be 14 on the right-hand side as a product. And so we would just add those together. We have 0, so 0 plus what equals 14. And then as far as our number goes, if we've got a 6 on the left-hand side and a -1 over here on the right-hand side, it would have to be a 7. So what we could see from this is that let's see, atomic number is what's mentioned first. Atomic number increases by 1, goes from 6 to 7, whereas the mass number remains the same. It stays at 14 in both cases. Okay, and I'm going to go through these kind of quickly. Here we just talked about electrons. Positrons are going to be just an antiparticle of the electron. It's a positive electron. So instead of being negatively charged, it's going to be positively charged. And just like before, it's really more proper to put that positive symbol right up there. And let's keep going. Alpha decay. Here's our alpha particle with a Greek symbol of alpha, or it's the same exact thing as the nucleus of a helium atom. We know that there's a mass of 14 and a charge of 2. We could go through those examples with numbers. We'll do that here shortly. What you should notice from this also is that these alpha particles are very slow moving. It's massive. It's got a mass of 4. That's larger than any of the others. So it's going to move pretty slow, meaning it's not going to penetrate very much. It can be stopped easily by paper, skin, or clothing. However, if they are ingested, they're pretty dangerous. And then the last one is not a particle at all because it has no mass, it has no charge. Instead, it is just purely energy. And we illustrate the fact that it has no mass or charge by the fact that it's got a 0 right there for each of those values. It does penetrate very well. It can only be stopped by by several feet of concrete or several inches of lead. And because it has no charge to it, it's not affected by any positive or negative charge. So now what we want to do, oops, what am I doing here? Now what we want to do is, you don't have this on your paper, but this is good practice to just go through and list all of those things that we just mentioned. So make sure that you know an alpha particle can be written like this. Either one of these values illustrate an alpha particle. Beta would be a mass of 0, a charge of -1. Well, that's exactly the same thing as an electron. A positron is a mass of 0 and a charge of +1. You can write that plus if you want, which we could also write like that. We could also say, we could write down information about a neutron. If you think about a neutron, it has a mass of 1 and a charge of 0. A proton has a mass of 1 and a charge of 1. We can remember about our zeros here for our gamma. Just making sure that you know those different particles, that's important. Okay, now we want to go through balancing and read through these. Essentially, you're just making sure that your mass and your charge or your number of protons are going to be the same, and you need to use a periodic table to help you identify some of these things. So here it says, A says, show the equation for alpha decay of polonium-214. So if I have polonium-214, that's part of how I'd write it. Then I'd look at my periodic table and I'd see that polonium is number 84. Well, it says that it's alpha decay, so I have to think to myself, where does the alpha particle go? And if it's decay, it's going to be on the right-hand side. So I'm going to write it like this, plus something else. So I do a little bit of math, and I know that on each side of this arrow, it has to equal 214 for the mass. So that means there must be a 210 up here, and this has to be an 82. So that means that it would be lead in this case. If we do the next one, we have bismuth 210, and bismuth has a mass, an atomic number of 83, and it says show the beta emission. So I'm going to emit a beta particle, which is going to be on the right-hand side. I can show it as an electron if I want. It has a mass of 0, a charge of -1. That means when I do that math, and again, I can't stress enough how much you really have to pay attention to some of these words. So now when I do this math, I see that it is going to be 210, and don't let this trick you. Make sure you get that math correct. It's going to be an 84 here. 84 plus -1 gives you that 83. So 84 is going to be polonium again. And then we have positron emission of arsenic 70. So arsenic 70, arsenic is going to be number 33, and we're emitting a a positron. So it's going to be a mass of 0, a charge of +1. So that means that we're going to end up having 70 and 32, which number 32 is going to be germanium. So that's how you go through balancing. And then here's one where it says electron capture by vanadium 70. So vanadium 70 is going to look like that. Electron capture, that's going to be a reactant. I'm grabbing an electron, so that looks like that. And then it results in a transmutation of, from 23 it goes to 22, which is manganese. And let's do the last few of these and then we will stop it. So this one is just going to go to 231 and 90, which is going to be thorium, I believe. Number 90, yes, number 90 is thorium. And then, so we've got 231 and 91, which 91 is going to be proactinium. And then finally, in this case, we're going to have 54. And then again, don't get confused with the negative signs. You've got that -1, which means this has to be a 25, which is going to be manganese. And that's it for this one.